Hello again, everyone. Welcome to 14.6 Dilations and Similarities. So I think in the last section I had said that, in the last video rather, I had said that in the next one, we would be talking about how to use similarities to address like some real world situations. We are going to do a little bit of that today, but we're going to do a lot more in the last and final lecture, which is coming next time. So today, we're actually going to focus we're going to take a step back and we're going to try to relate similarities and congruences even more. Um, so remember, the big picture is that congruences tells me shapes look the same and are the same size. Similarity says they look the same, but maybe they're not the same size. And if you remember, when we first talked about congruences, we actually defined what it meant to be congruent in a really rigorous way. We said that if you're going to be congruent, we need to use our transformations: translation, reflection, rotation. And if you remember, I gave you this example and I was like, are these two shapes congruent? Are they the same shapes? And the answer was yes. And I could literally pick one up, bring it over, rotate it around, and that showed me that the two shapes were indeed congruent. And so we were able so even though we have a notion of congruence being that these two shapes are the same, um, we were able to use our transformations to argue it mathematically. And so my question is the same for similarities. We have a way to detect if two shapes are congruent using transformations. Can we do that with objects that are similar? The answer is yes, but we have to add a new transformation called dilations. So what is a dilation? So dilation's yet another transformation. So we have three so far: translation, reflection, and rotation, but there is actually more transformations than what we've talked about so far. To dilate something, we're given a point to be the center of dilation. We're given a number k to be the scale factor, and we're finally given an object that we want to dilate. And what happens is, for any point A in the object that we want to dilate, so at any point, we draw a line from P to A and scale the length of that line by K. So here's our example. Here's my shape that I want to dilate. And next to it is the center of dilation, P. And I want to scale everything by a factor of 2. So what are we supposed to do? So this is what we're supposed to do. According to what it says up here, for any point in the object, we draw a line from the center of dilation, which in this case is P, and there is our line of dilation. And whoa, in order to dilate the picture, we scale the length of the line by K. So right now, all I'm saying is, since K is 2, what I want is to make a duplicate of this line. So it goes over 4, and it goes up 2. And that is the location of our new point, A prime. Okay, so I have to do this for every point in the object. But for similar reasons to other things we've discussed, I only really need to do this for the four points that I've labeled in this picture: A, B, C, D. So if I do that for B, here is the line from P to B. So I'm just going to go ahead and double its length. And that's going to be where the point B prime lands. There's the line for C. It's 4 units long, and so I've got to now make it 8 units long because my scale factor is 2. Sorry, that line became black. I'm just going to leave it. No, now it's bothering me. I don't want to leave it. There, now it's perfect. And then I don't want the picture to get too busy, so you can do the same thing for D. Oh, I made it black again. Okay, now I'm leaving it. You can draw a line to D and get that D prime's here. So now I'm going to get rid of these dilation lines, because I just don't want the picture to get too busy or confusing. But that's how you get the new object, and now the question is, okay, well, what about this point and that point and that point and so on and so forth? And the point is that we can just assume once we have these 4 outside points, everything else works nicely. So indeed, we end up with this shape. Okay, and that's it. This is the output of this transformation. So with k equals to 2, a center of dilation P, and an object to dilate, we basically, this guy right here, that is the dilation that we got. And as a quick note, k doesn't have to even be a number that looks like an integer like 2 or 10. It can be a decimal, it can be a fraction smaller than 1, it can be any number you want. When you dilate by a number smaller than 1, you actually make the shape smaller. You might have noticed when the word dilate, you maybe are thinking that it would make something bigger, which is correct in general, but it can also make things smaller. Okay, so this is dilation, and so why do we care about dilations? It works out that they scale the distances in your picture by your scale factor. That is, the dilated object has to be similar to the original one. And so you can see that visually, right? In my dilated object versus the object I wanted to dilate. Um, we can see that the objects are the same shape and they're just different sizes. You can also see how the distances are. So remember when we defined similarity, we gave like 3 or 4 different definitions, but the most formal one was that distances are scaled by the scale factor. So notice the distance from B to D here is 2. And over here, the distance from B prime to D prime is 4, 2 times that length. And then notice from A to D, we traveled across a diagonal of 1 square. But from A prime to D prime, we travel across the diagonals of 2 squares. And that multiplication by 2 is really coming from the scale factor. So in fact, dilation is this kind of 4th transformation we need in order to scale things, because for similar objects, they could be larger than the other. So finally, we have I know, yes, yet another definition for similar objects. But what's nice about this definition here is that it is similar to how we define congruent objects. So 2 objects in the plane are similar if at least one of translations, reflections, rotations, or big important thing, dilations, are needed to take one shape to the other. So notice that if I was to, get rid of this part of the definition, what do I have? At least one of translation, reflection, rotation, then I would really be talking about congruent. 2 objects are congruent if you just need a translation, reflection, or a rotation. But if you want 2 objects to be similar, then you need to add in dilations, because similar objects can be bigger than the originals, and so we have to allow for a way to stretch things out, and that's what dilations do. So here's our friendly cat again. Why are these pictures similar? Well, I can start by translating my shape. Come on, play nice. Ah. This was working nicely before. Come on. Come on. Maybe we have to zoom in and trick it. What if I move you up? There we go. Take that, technology. All right. So I translate the picture right. And then I'm gonna do a rotation twice by 180 degrees. And then I'm going to pick this point right here, and I'm going to now dilate the picture. And so what happens when we dilate? The distance from the yellow point to this black point doubles. It goes from here, and then I double it, and so that gets sent there. The distance to this point doubles, so it goes from there to there. And then likewise with the height, we double it and it gets sent to there. And so the point is that the picture gets stretched until it lands right on top of the other picture. So the point is that the two pictures I have are similar because I can use some combinations of translations, reflections, rotations, and dilations. So dilations are this fourth transformation we need to show any two objects are similar, but that doesn't mean we don't still need translations, reflections, and rotations. So here I've just written down what we've done. We translated right by so many units, we rotated by 180, and then we dilated from the top left corner by a scale factor of 2. Okay. So let's do an example together now. Let's say we dilate the below grid so that it becomes 15 centimeters wide, and I didn't really say where we're dilating, so let's say it's right here. So we've got this, and I'm gonna get rid of the grid lines now. These are no longer helpful for us. So we've got this grid, we've dilated it so that from this point, so that means we're stretching things out like that. And we've done this so that the spacing is no longer 1 centimeters on the grid. Or sorry, rather, when we do this to get that it's 15 centimeters wide, the spacing will definitely not be 1 centimeter by 1 centimeter anymore, right? So just to make this very, very clear, what I'm really saying is I'm taking this picture and I am literally dilating it. I'm like stretching it and making it bigger and bigger. And so the point is, these dimensions here are no longer 1 centimeter. They're much bigger than the original picture, right? There we go. So these distances are now kind of a question mark. And the point is we made it so that the width became 15 centimeters long. So the spacing will no longer be 1 centimeter. What will it be? So we dilated this so that the width is now 15. How wide are these boxes now? That's what the question is asking. Okay? So notice the current width without dilation is 2 centimeters, right? Or actually, let's not do it this way. I think the picture I had before was actually way better that I decided to erase for some reason. Um, the point is now in the bigger version of this grid, this new width is 15, right? So how wide is each square length? Well, we can see that we now have kind of two groups. This whole length here is the length of 2 blocks, right? So 15 over 2 gives us 7.5 centimeters as the width of your grid. Because if this length here is 15, then I have to break it up over 2 different pieces, okay? You can also think of this as the new length is 15, the old length was 2, and so we scaled that by a factor of 7.5, and so we scale 1 by a factor of 7.5. Okay, how tall is the grid? Well, if each side length is 7.5, I just now have 3 of those. So I've got 7.5 times 3, which should equal to 22.5 inches. It's 7 times 3, which is 21, plus 3 times 5, which is 1.5. And this is basically all I'm expecting for 3B. It does, 3B asks for a lot on the homework, and I don't really need you guys to dwell on all those extra parts of the problem so much. I do want you guys to try 4B, specifically the part about finding a relationship between X and Y, I think it says. Sorry, I'm looking at the book. Yeah, it says, how are X and Y related? I do want you to try it, but don't spend more than, if you spend more than 5 minutes trying to find the relationship, just move on. It's worth doing. The reason I'm being laxed about it is it technically uses a skill from 302. So if you've done 302, definitely try to do it. But I still think you can figure it out even if you haven't taken 302. Okay? But otherwise, I don't want you to do all the extra questions that are asked in problem 3B. Okay. So that's dilations and all that good stuff. So when we were testing for triangle congruence, we didn't end up actually using translations, rotations, and reflections, right? We know that we say two things are congruent if we use these two things to transform them, but we didn't really end up using that when we needed to show two triangles are congruent. We had these really convenient 3 tests: side, 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 and angle, side, angle. If two triangles have the same 3 sides, have two of the same sides with the same angle in between, or they have two of the same angles with the same side in between, we know they're congruent. So now there's a question of, is there something similar for triangle similarity? And so I've drawn 2 similar triangles here, and I have suggestively color coded the angles, and I just want to show you something interesting. Look at what happens if I impose the 2 purple angles with each other. These angles are the same, right? Remember, so this was actually, I think this was actually the very first homework question. Just because one angle looks bigger in terms of how long the sides are, that doesn't mean one angle is bigger than the other. The angle is measured by the distance between that rotational distance between 2 lines. And so these 2 angles are the same. And these two angles are the same. And those two angles are the same. So notice that two similar triangles have all three of the same angles. And in fact, that is enough to say that two triangles are similar. If two triangles share the same three angles, they are similar. That means that if two triangles have the exact same angles, then I must be able to use translations, rotations, reflections, and maybe dilations to get one to lie perfectly on top of the other. That's a really powerful statement to say that two triangles are similar to each other. Saying they're similar literally does mean I can like stretch it out to make them look exactly the same. And I'll also remark that this AAA, angle, 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 does not work for quadrilaterals and other shapes. For example, last time we talked about how a square is not similar to a rectangle because their proportions are different, but both of these shapes have 490-degree angles. So these congruence tests, sorry, I always forget their names, congruence relations that we have, they only really work for triangles, and that's something really important I want you guys to remember, is you can't apply these things to other shapes. AAA, SAS, SSS, and ASA only apply to triangles. The reason this works out, the reason that AAA is true, is that none of our transformations ever change angles. If you translate something, if you just move it around, that's not going to do anything to the angles. If you rotate it, if you reflect it, angles stay the same. The only one that maybe is confusing is dilations, but that also will not change the angles. All right, let's do a practice problem. Are these triangles similar? ADE, which is this big one, and ABC, which is this smaller one. So by similar, what do we really mean? We mean is one a stretched out version of the other. So you could look and probably say, yeah, these look similar in at least the English sense, but it's a little bit harder to be able to tell that this is really, really true. And so what we want to do is try to use this congruence tool we just learned, AAA. So let's try to do it. So notice, I'm trying to avoid using yellow. Notice angles ACB equals AED, since both are 90 degrees, right? We can see ACE, which is this guy, has a 90-degree marker, and same with ADE, or sorry, AED. Okay. Also, notice these pictures, they're lined up right on each other perfectly so that CAB equals DAE, right? This angle right here is literally the same thing as that angle right there. It was drawn so that those angles were given to you for free. So the last question is, are these two angles the same? I want you to pause the video really quickly and try to figure this out. Spend no more than maybe a minute. Okay, so are the two angles equal? The answer is yes. And the reason is, so instead of writing CAB and ACB, I'm just going to give us some nice names to deal with. So this will be little a, this will be little b, this will be little d. Okay? Notice that actually, let's not do it this way. Let's do it like this. So there is some magical things going on here. In particular, because this side here and this side here are both perpendicular to the bottom, this is kind of like an extra fact. This isn't very, very clear, but I wanted you guys to try to wrestle with this and see if you could figure it out. This side is indeed parallel to that side, right? They're both perpendicular to the bottom, so they're both sticking out straight. So now I want to draw very long lines. And I'm going to draw a little parallel marker. And I'm going to extend this line as well. And now ignore the triangle for just a second. This setup should look familiar. This is the parallel postulate in play. I've got this transversal T. I've got two parallel lines, M and N, and B and D are corresponding angles. So we can actually say that B equals D, or in other words, if we're going back to our notation, CBA, angle B, equals EDB, angle D, sorry, EDA, there we go, are equal because BC and DE are parallel. So by the parallel postulate, corresponding angles are equal. And we can see from the picture that angles B and D are corresponding angles. I bet you were not expecting parallel postulate to come out of nowhere. You can now see a really good reason for why mastery is a really important system that we have in place. I really want to make sure you guys are keeping on top of this content and not just leaving it behind. With traditional exams, it's really easy to say, well, I didn't get that content, whatever. Mastery is meant to help you because especially in math, content builds on itself, and I want you guys to feel like you can master all of this content. Okay. So anyways, what was the point? Did we even answer the question? Are these triangles similar? So the answer is yes. So yes, similar, sorry, ABC is similar to ADE. By what fact? By angle, angle, angle. Because we just showed that all three angles of the triangles are equal. So that means I can take one triangle and I can scale it up to be the other one. And you could probably tell that from the original picture, but now we've proven it using, simple facts like two angles are literally the same. But then for this last one, we had to use some very heavy machinery. Like I said at the beginning of this chapter in 14.1, this chapter uses a ton of tools from 10.1, which is why I suggested people review them if it's been a while. Okay, so now let's use the fact that these triangles are similar to our advantage. I've labeled some dimensions. AC is 12, AE is 18, and BC is 10. Can I find DE? The answer is yes, because we know ABC is similar to ADE. Which means we can find the scale factor for these two triangles. We can see by what factor ABC was scaled to get ADE. Remember, the scale factor here is acting like how I scale an image, right? The two cats that we talked about last time was scaled by a factor of 2. So what is K? how much larger is ADE than ABC? Well, I can just use the fact that I know the two lengths of the bottom sides, right? We scale the picture by 18 over 12, which is 6 divided by, oops, sorry, which is 3 over 2. Yep, there we go. Okay, so we've never really had a scale factor that was a fraction before, but notice 12 times 3 over 2 is indeed 18. So it's fine for scale factors to be fractions. We usually think of them as whole numbers because we can think about, it makes sense to us to think about what it means to like scale a picture by a factor of 2 or by 10, but you can also scale it by 1.5. You just make it, you add half of the size to the lengths of everything. So what does this mean? So DE, if ADE is a scaled version of ABC, the side length DE should be K times the length of BC. But we know the length, we know the scale factor is 3/2, and we know BC is 10. And so this means that DE needs to be 15 feet. Okay, so similar triangles knowing things are similar is pretty handy because we can find the dimensions of things. We did lots of problems like this last time, but now we're using them in the setting of similar triangles. So here I used the internal factor, or I used the scale factor method to solve this. I could have also used the internal factor method by doing 12 divided by 10 and doing stuff from there. But I think the scale factor method's a little bit more natural. At least for me. The reason I think it's more natural, if you're not sure why I'm saying that, I'm not saying it's like the easier thing to do. I'm just saying that when we're talking about similar objects, scale factors tell us how things scale. Okay, here's a problem for you to do. Show that these triangles are similar. And I do need to add some extra information. And this extra information is going to really be a hint. Sides DE and BC are parallel. Spend 3 minutes, pause the video, try to show these triangles are similar. Hint, hint, use angle, angle, angle. Okay, so right away, the first thing I see when I look at this picture is I see opposite angles, and I like opposite angles. So DAE, angle DAE equals BEC. This is getting maybe a little confusing because we use DAE to refer to the triangle. I kind of probably did that somewhere else as well. Let's just give these names, shall we? Let's call these A and A prime. A equals A prime since opposite angles are equal. Okay. And now we have two more angles. I'll call this little d, little e, little b. This will be little c, which means this needs to be a much bigger c. Okay, so did you guys try to use parallel postulate? So there's the line, there's a line, and I will think about this transversal first. Okay, so I've got my two lines and a transversal. And now the point is that because of the parallel postulate, angle B corresponds to this angle right here. right? So B equals E using parallel postulate, and also the fact that, again, opposite angles are equal. And then it's not too hard to believe that D equals C for the exact same reasons. So we've shown A equals A prime, D equals C, and E equals B. All the angles are the same. So by AAA, the triangles are indeed equal. Yay. Let's get some water. Cool. So if you're a little rusty on these skills, these problems might be a little bit daunting. But once you get the hang of them, they're kind of the same things over and over. It's try to draw some lines, try to see parallel postulate or opposite angles. You're basically turning this problem into learning objective one. Again, I'm emphasizing how important it is that we are trying to master these concepts. Okay, so far I haven't really given you any applications of similarity. Where does similarity get used in the real world? How is it useful? So if you haven't ever done this before, this is something I recommend you do. I mean, I don't know about you guys, I'm in Lincoln and sometimes it's cloudy, right, in Lincoln, especially with colder weather, but hoping that it's a little bit sunnier when you're watching this. There's something I used to do as a kid that I recommend you try to do. Maybe it's better at night to do, but when I was a kid, I would like look up at the moon. I would see the moon, and I knew in my head that the moon was huge, right? I knew that if the moon was literally in front of me, like I could easily get squished by it. But when it's so far away, it's so small that if I held my thumb in front of me just right, I could cover the moon entirely with my thumb. And I thought that was like, it felt kind of funny, like, haha, my tiny little thumb is bigger than the moon. Obviously, I understood what was going on. I'm sure a lot of you guys have observed similar phenomena in real life where something is so close to you that it's covering something really, really huge that's really far away. So if you've never done this, you can do this in your room, just or in your house. Just look around the house, look for something really, really big in comparison to the size of your thumb, and then hold your thumb in front of that object. You might have to close one eye as well, and do it so that your thumb covers the object entirely. I know this maybe sounds a little silly. I do want you to actually pause and spend a minute and just find something. It could be as simple as a water bottle and try to do it. You might have to bring your thumb really close. So this phenomenon, this thing is that you're doing leads to a tool for measuring distances called sighting. And that's what I want to talk about. You can use this phenomenon to actually measure how far away things are from you, which is kind of really, really cool. So let's say in the distance, we see a 10-foot tall light pole. You manage to cover it entirely in your line of sight with your 2-inch tall thumb by holding your thumb 10 inches in front of you. So this is where it's, again, I know it sounded silly, but if you didn't do the thing where you hold your thumb out in front of you and cover something, do it so that you understand really what this setup is doing. Because if you've never tried it before, it's going to seem really weird. So just from this information alone, can we tell how close the man is? The answer is surprisingly yes. And so here's a drawing of the scenario. We've got our eye, our hand is 10 inches in front of our face, and then our thumb is 2 inches tall and And in the distance, we see this little light post that is 10 feet tall. So this is a nice drawing, but I want to turn it into a math drawing in order to do stuff with it. So the eye is just going to be a small point. And then those two red lines, I'm just going to draw out like this. And then here is my 2 inches. And here is my 10-foot long pole. So I'm going to go ahead and underneath it in blue write 120 inches. Oh yeah, and also we know some other distances, right? We know that this length here, it's really this length here, right? But I'm drawing it there to be a little suggestive. Actually, that doesn't actually really help us much. You can draw it there if you want. It doesn't really matter. I think I'll actually draw it here. Okay. The triangles are similar. The ones I just drew, those are similar triangles. Why are they similar? Pause for exactly 30 seconds, and I want you to scroll back up and look at the first example I did. Or first problem we did. Let's just do it together, shall we? First example. Think about this one. Why did this one work? Take 30 seconds, think about it. So what made this scenario work was that the triangles shared an angle in common already. That was easy. But also we were able to use the parallel postulate because these two sides were equal, and we were able to deduce that these angles were the same. Now you might say, oh, we also knew these angles for free, but it works out that even if I didn't tell you those angles, you could have still used the parallel postulate with the same reason, but using this line as the transversal to show that these two angles actually were forced to be the same by this construction. Really, it comes down to having these two lines being parallel. So this is a fact that you are allowed to abuse so long as you quote it. But you can only abuse it in this setting. So I want you to say this. Both triangles share an angle, right? If we look, this is the angle both triangles share. And so what about these other two angles, right? So this is the sentence that I think I'd like you to write when you are solving similar problems like this on the homework. And the other two are equal by parallel postulate. But what do we need to be assuming in order to use parallel postulate? Assuming the thumb is parallel to the light post. And so when I say the other two are equal, I'm really saying the other two are equal to their corresponding angles, right? I'm saying those two are equal, these two are equal, and then that third angle are literally the same angle. That's the one that they share. And so by angle, 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 these triangles have to be similar. All right, so with this, I claim, sorry, you might be still copying this down. So with this, so remember, what was the point of this problem? This problem was asking us how close, oh no, I'm sorry, I just caught this now. I said, how close is the man? I guess you could interpret this problem differently. And originally, this was a man, not a light post. This is supposed to be the light post. I was not making the assumption that you are any particular person. Sorry about that. Okay, so how close is the light post? How do we use similarity to do this? Well, we can do this in two different ways. Because the triangles are similar, we can use our scalar factor method and our internal factor method to solve this problem. So to use a scalar factor method, remember the scalar factor tells us how much we scaled one dimension to get the new scaled version of our object. In this case, the only two things we see in common are these 2 inches and this 120 inches right there. So what is the scale factor? If k is the scale factor, k is 120 divided by 2, which equals 60. So that's the scale factor. Okay, these triangles are similar. So if that small length is 10 inches, let's call this L. Then L, to find the length of the big triangle, to find how long that distance is, these triangles are similar, so the proportions should scale similarly. If 2 inches is scaled by 60 to get 120 inches, then I've got to also scale 10 by 60, the scale factor, to get 600 inches. That means the light post is 600 inches away. So I don't know if you guys are like, how you feel about this and the content, but to me, this is kind of mind-blowing. You need to know such small amount of information and you can just deduce how far away something is just by using your thumb in some basic distances and the fact that we have similar triangles. I think this is a really crazy thing that we're able to do. And it works because of geometry. So cool, awesome. That's using the scale factor method. What about the internal factor? Well, remember, internal factor is where you compare the dimensions of the same shape in order to figure out how the two quantities are related, and then the two quantities of the larger version have to obey that same relationship. So remember that there is some nuance into whether we do 10 divided by 2 or 2 divided by 10. But the point is that we're looking for the length between, or the height rather, of the triangle, of this longer triangle. So I need to know how this length compares to that length. So if I need to say, how does L relate to this? I need to ask, how does 10 relate to 2? You guys see that careful process? If I want to know how this relates to this, I figure out how this relates to this. And the point is that the length of these triangles is 10 over 2 equals 5 times the base of the triangles. So L also equals 5 times 120, which is, yes, indeed, 600 inches. So there's a second way to solve that problem. Okay. So one thing I will comment on is how important it is that especially when I was doing this problem up here, I kind of very quickly just remark that, oh yeah, I need to make this into 120 inches. This first way wouldn't have worked if I didn't convert it to inches, because this top number is inches and this bottom one is, or sorry, this, if I had left this as my, as 10 feet, down here, this is inches. Dividing feet by inches doesn't really make sense. So I really had to convert it here. If you hadn't converted it here, it would have still worked out. Your answer would have just been in feet instead of inches. And so on the similar homework problems, this is kind of like what I'm expecting when they might say something like, use two methods to solve this problem. These are the two methods that you have to do these two problems. Okay, let's do one more example. We see a 6-foot tall man in the distance, and we know this time how far away he is. So by the way, this is the example that messed up my wording of the prior problem. A 3-foot girl stands between you and the man so that she just perfectly covers the same height as the man. So you're imagining that she is standing at a certain distance so that she blocks the man perfectly. That's how close she is to you, that you can't see the man in the distance anymore. So it's like the same idea as the thumb, but instead of a thumb, we have this girl. The question is, how close is the girl? So here's our drawing of the scenario. We've got our 6-foot tall man. We have our 3-foot tall girl. And we have that distance of 10 feet. Let's change this into a math drawing. And so this is 10 feet. This is 6 feet. And this is 3 feet. The reason that I've drawn it like this is that the dashed lines here, I kind of neglected to mention this before, which maybe, I don't know if this, I was hoping this was clear, but the dashed lines are supposed to be like your line of eyesight. So anything inside this triangle is what you see. So right now the girl is completely blocking the man, just as up here, how your thumb was completely blocking the light post. So what do we do? Well, these triangles are similar, right? By the same reasoning in the prior problem. So on the homework, at least the first time you write it down, if you're going to say the triangles are similar, do go through the process of explaining this. And so what does this mean? The scale factor, k, we can use the fact that we know the base of this triangle is 6, the smaller one is 3, so the scale factor is 2, which means this shorter length right here had to be scaled by a factor of 2 in order to get the bigger length of 10 for the big triangle, which means that that little girl is 5 feet away from us. So that 5 tells us how far away she is. So I did that a little fast, but it's using the similar tools to the prior problem. And the reason I'm doing this problem is that on problem 9, problem 9 on the homework, this setup is meant to be similar. This is meant to give you just a little bit of scaffolding for that problem. It's not exactly the same. The problem's still a little bit more challenging. But basically, instead of a 3-foot tall girl and a 6-foot tall man, you have a 25-inch and a 50-inch television. And the problem is asking you, gives you arbitrary distances for how far away the 25-inch TV is and how far away the 50-inch TV is. So it's a different problem. But if you ignore those distances they give you in the problem, if you, or maybe you keep the one with a 50-inch TV and then pretend like you get to select where the 25-inch TV is, and you redo this problem, you redo this process, this process will tell you where to put the 25-inch TV, where it needs to be in front of you, so that it looks like the same size as the big TV. So the idea is, you're given this problem, you're given like the TV is like this distance, the 25 inches that distance, the 50 inches that distance, and what I'm saying you should do is forget about where the 25 inches, figure out where this needs to go so that it would cover that 50-inch TV perfectly. And I claim that once you do that, then you can address which one would look bigger. Okay, so maybe not as well explained, but my point is try to use this technique that you can figure out how close something has to be in order to cover something else, in order to figure out how to answer that question. That question's still a little bit more challenging, but I'm hoping that this kind of helped. Okay, so that is dilations and symmetry. So dilations give us a way to use transformations to construct two similar objects. And from there, we were able to characterize triangle similarity using our angle criterion, which can help us solve some real world problems that just literally involve your thumb, which is pretty cool. All right, that's it.